Hey everyone, before we dive into today's topic, I need you to think about something. What if I told you that three steel parts with the exact same chemical makeup could have completely different properties? One soft and bendable, another hard and brittle, and the third strong and tough. Sound impossible? Stick around because we're about to explore the fascinating world of steel heat treatment, and by the end of this video, you'll understand how temperature alone can completely transform this incredible material. Let's get into it. Why steel dominates modern engineering? Steel accounts for over 90% of global metal production, and that dominance isn't just about strength or affordability. It's about something truly unique, the ability to completely transform its properties through heat treatment. This superpower makes steel the most versatile engineering material we have. The building blocks of steel. Steel is fundamentally an alloy of iron and carbon, usually with a few other elements mixed in at small proportions. We classify steels based on their carbon content into three categories: low carbon, medium carbon, and high carbon steels. Anything above 2.1% carbon crosses over into cast iron territory. When a steel contains significant amounts of other alloying elements, typically above 1%, we call it an alloy steel. Otherwise, it's a plain carbon steel. Understanding iron's temperature behavior. To grasp how heat treatment works, we need to understand what happens to pure iron at different temperatures. At room temperature, iron atoms arrange themselves in a body-centered cubic structure, with one atom at each corner of the unit cell and one in the center. We call this arrangement ferrite. When you heat iron above 912 degrees Celsius, something remarkable happens. The atoms shift from that body-centered cubic structure to a face-centered structure, where they pack more closely and efficiently. This face-centered cubic form is called austenite. As temperatures continue rising, iron changes back to ferrite at 1,394 degrees before finally melting into liquid at 1,538 degrees. The iron-carbon phase diagram. When we add carbon to iron, things get more interesting. The iron-carbon phase diagram shows us how different phases within the material change with varying amounts of carbon. Carbon atoms are small enough to fit into the spaces between iron atoms, but here's the catch: the body-centered cubic structure of ferrite can only accommodate a tiny amount of carbon, about 0.02% by weight at 723 degrees. That's roughly one carbon atom for every 1,000 iron atoms. When the alloy contains more carbon than ferrite can handle, a new phase called cementite forms alongside the ferrite. Cementite is a hard, brittle compound made up of one carbon atom for every 3 iron atoms. Austenite, on the other hand, can hold much more carbon than ferrite, from 0.8% at 723 degrees to 2.1% at 1,147 degrees. This works out to roughly one carbon atom for every 10 iron atoms. The magic of perlite. For an alloy containing 0.8% carbon, something special happens. While cooling, the structure remains austenite until it reaches 723 degrees. At this temperature, the austenite undergoes a transformation, and the excess carbon combines with iron atoms to form cementite. These two phases create a distinctive microstructure with alternating layers of ferrite and cementite, called perlite. This 0.8% composition is special because the austenite transforms entirely and simultaneously into ferrite and cementite, producing only perlite. We call this the eutectoid point, and steel with this composition is called eutectoid steel. In steels with less carbon than this eutectoid composition, some ferrite forms before reaching the eutectoid temperature. The final microstructure ends up being a mix of ferrite and perlite. In steels with more carbon, cementite forms first, and the final microstructure becomes a mix of cementite and perlite. Time-temperature transformation diagrams. All these transformations rely on diffusion, the movement of carbon and iron atoms through the lattice to form new phases. Since diffusion takes time, the basic phase diagram only represents equilibrium conditions where heating and cooling happen slowly enough for atoms to fully rearrange. In reality, complete transformation can take minutes, hours, or even days, depending on composition and temperature. This is where time-temperature transformation diagrams come in. These diagrams map out the relationship between time, temperature, and the phases that form in a given steel. The game changer, martensite. The most important non-equilibrium phase is martensite. It forms when austenite cools so rapidly that carbon atoms don't have time to diffuse out of the face-centered cubic structure to form cementite. The structure wants to transform to body-centered cubic, but can't because of the trapped carbon atoms, so it distorts into a new body-centered tetragonal structure called martensite. This transformation happens almost instantly, growing out from austenite grain boundaries and propagating at close to the speed of sound. The result is extremely hard and strong, but also very brittle material. The trapped carbon atoms strain the lattice, locking the structure in place and blocking the motion of dislocations. More carbon means greater lattice distortion, which increases hardness and strength at the cost of increased brittleness. Understanding microstructure variations. By manipulating time and temperature, we can achieve a whole range of microstructures. Above the transformation temperature inflection point, we get perlite. At higher temperatures, the transformation proceeds more slowly, giving carbon atoms time to move over longer distances and resulting in coarse perlite. At lower temperatures, carbon atoms have less time to diffuse, so the structure forms quickly as fine perlite with closely spaced layers. Fine perlite is stronger than coarse perlite because the hard, brittle cementite layers are more closely spaced, creating effective barriers to dislocation motion. Below the inflection point, diffusion distances are even more restricted, allowing a different microstructure called bainite to form. This is still a combination of ferrite and cementite, but with a much finer, more irregular mixture. Bainite offers an excellent balance of strength and toughness, making it a target in some heat treatments. Continuous cooling transformation diagrams. In practice, steels aren't usually cooled to a fixed temperature and held there. They're cooled continuously down to room temperature. Continuous cooling transformation diagrams show the phase transformations that occur with these more realistic cooling conditions. Different cooling rates produce different results. Cool steel rapidly at 200 degrees per second and you'll obtain martensite. At 50 degrees per second you'll get a mixture of perlite and martensite. At 10 degrees per second you'll get pure perlite. The diagram shows how difficult it can be to obtain martensite. Plain carbon steels often require very high cooling rates that aren't achievable in practice. This is one of the main reasons we add alloying elements like nickel and manganese. They shift the transformation curves, allowing martensite to form at slower cooling rates. The 4 key heat treatment processes. Annealing. Annealing makes steel soft, ductile, and easy to work with. It's often applied after forging or casting to relieve stresses and make the part easy to machine. The process involves heating the steel into the austenite region, then cooling it very slowly inside the furnace. The gradual cooling gives carbon atoms plenty of time to rearrange into the wide layers of coarse perlite, which has low strength but is very soft and ductile. Normalizing. Normalizing is similar to annealing but uses a slightly higher temperature and air cooling instead of slow furnace cooling. The higher temperature better eliminates irregular microstructure left over from previous processing steps. The faster cooling rate produces a fine perlite structure that's stronger and harder than annealed steel while still retaining useful ductility. This process resets the steel to a uniform, fine microstructure with good strength and hardness. Quenching. Quenching involves very rapid cooling, usually by plunging the steel part into water, oil, or another medium. The objective is to produce martensite. The quenched steel has high hardness and strength but is far too brittle for most applications. Tempering. Tempering is the follow-up to quenching. The quenched martensite steel is reheated to temperatures between 200 to 600 degrees Celsius, below the levels needed for austenite transformation. It's held at this constant temperature for a defined period, anywhere from a few minutes to several hours, before air cooling. During tempering, excess carbon atoms trapped in the distorted martensite lattice diffuse out and combine to form extremely fine particles of cementite. This allows the lattice to relax back towards a body-centered cubic ferrite structure. The resulting tempered martensite greatly improves ductility and toughness while retaining much of the strength and hardness thanks to the finely dispersed cementite particles. Steel in this quenched and tempered condition is usually referred to as hardened steel. This process is used for critical parts that need high strength combined with toughness, like crankshafts, high-strength bolts, tools, or heavy-duty structural components. The challenge of hardenability. The objective of quenching is to cool the material fast enough that austenite turns into martensite through the entire cross-section. This can be challenging with thick components, where the core takes longer to cool than the surface, resulting in perlite or bainite forming instead of martensite. Hardenability quantifies a steel's ability to form martensite to a given depth during quenching. The Jominy end quench test is the standard method for measuring this. It involves heating a cylindrical steel sample until it's fully austenitic, then quenching one end with a standardized water spray setup. This creates a controlled cooling rate that decreases as you move up the sample. Hardness measurements taken at regular intervals create a hardenability curve. Maximum hardness is governed by carbon content, but the rate at which hardness decreases with distance from the quenched end is mainly influenced by alloying elements. These elements allow martensite to form at slower cooling rates, resulting in high hardness even deep into the part. Steels containing nickel, chromium, and molybdenum are classic examples of alloys with excellent hardenability. Surface hardening techniques. Sometimes we don't want the entire component hardened. Instead, we might only need a hard, wear-resistant surface while keeping the interior tough and ductile. This is common for components like gears and shafts that experience high contact stresses but also need to resist impact loading. Induction hardening and flame hardening involve directly heating the surface of the component, followed by quenching to create a hard martensitic layer. But these methods only work effectively in medium or high carbon steels. For low carbon steels, case hardening techniques that actually alter the surface composition work better. Carbizing involves heating the part in a carbon-rich environment to increase surface carbon content, followed by quenching. Nitriding introduces nitrogen into the surface to form hard nitride compounds without needing quenching, which avoids any warping that can occur with quenching. Bringing it all together. In practice, heat treatments like annealing, normalizing, quenching, and tempering are combined into sequences along with forming and machining steps. Each stage of the manufacturing process prepares the steel for the next, until the final form is obtained with a microstructure that provides the desired balance of strength, hardness, and toughness. If you found this deep dive into steel heat treatment helpful, make sure to hit that like button and subscribe to HowToHub for more engineering and manufacturing content that breaks down complex topics into understandable explanations. Got questions about heat treatment or suggestions for future topics? Drop them in the comments below. We read every single one and use your feedback to create the content you want to see. Until next time, keep learning and stay curious.